So now I'm going to show you how to design the peak current mode control for the buck converter with SmartCtrl software. In this example, the current mode control is based on controlling the output voltage of the DC-DC converter through the control of the inductance maximum peak current. There are some commercial PWM IC, such as the UC 1842, that implement this type of control. So in the SmartCtrl, you have the buck converter is included in the predefined topology, and also the control structure is the peak current mode control. After we design the control, we export the results to PSIM simulator in order to check if our control that we design is stable. So let's start with the SmartCtrl. So in this case, I open the SmartCtrl software. I go to File, to the initial dialog. Click on. This is the initial dialog window. And here you can see in the predefined topology region, you can find the DC-DC converter for the peak current mode control. If you click on this icon, this is the design flow. And here, the first step, I have to select one of the plant. Here you can find the buck converter, bus converter, buck bus, flyback, and forward. In this case, I chose a buck converter. So after that, here, you can define all the input parameters. So here we have the input voltage, the inductance, capacitance, output power, switching frequency, and output voltage. And in the left side, we can see all the steady state DC operating point. So here you can check if with these values, your converter is operating in continuous conduction mode or discontinuous, for example. Also, you can see the duty cycle, and this is the ripple of the inductance currents. So after that, also, if you change any of the parameter, for example, if I set 10 volts, if you click on calculate, also the steady state DC operating point are updated. So in this example, I left to 12. Also in the waveforms icon, you can see the steady state waveforms. This is the inductance current, and also the current through the MOSFET. After that, I click on OK. So I have to define what is the gain of the current sensor. In this case, I leave 0.2. So click on OK. And now it's time to define some of the modulator parameters. So if you click in this icon, also you can define the slope for the compensation ramp here. This is the slope of the compensation ramp, because in this type of modulator, or this type of controls, the duty cycle is limited by the 50%. So if you want to increase the duty cycle, you have to use a compensation ramp. So in this case, I left 1 kilo in this section. The S end represent the inductor shear slope, and the SF represent the shear slope for the inductor current. The attenuation is some gain that is applied to the control, to the output voltage. So after that, we have to click on OK. So now it's time to define the other loop. So here we have to select one of the voltage sensor. In this case, I select the voltage divider. Here we have to define the VRF, the reference voltage, and here if you click on calculate, you can see the gain of your sensor. So if click on OK, after that I have to select one of the compensator. In this case, I select the type 3, and also you have to define the resistor, because we used this value of the resistor in order to calculate the other passive components that the type 3 compensator has. So click on OK. And now I have to select one point of the solution maps that I mentioned before. The solution maps represent the relationship between the crossover frequency and the phase margin. So in this case, I select one point of the solution maps, for example, 2 kilohertz for the crossover frequency and 90 degrees for the phase margin. After that, if I click on OK, also I have to click on OK. So now this is here we can see the frequency response of the open loop transfer function, and also in the green trace you can see the converter plant frequency response. Also here you can see the transient response in small signal, and you can see here the steady state waveforms of the converter. So the last step is to export directly to PSIM. In this case, if I go to this icon, I select the two PSIM schematics, and then I have to define one name. Maybe I set test number 1. Click on open, and here you have to select the components, the passive components. Click on OK, and now the simulation is open. So maybe let me close this. In this case, this is the power stage of the buck converter. Here we are sensing the current through the MOSFET. This is the gain of the current sensor, and here we have the comparator for the current with the control signal for the peak current. So I set a voltage proof here. I call this point is sensed, and also this is the I set V control in this case. So I click on simulate. Okay, this is let me show you. So here is the output voltage that achieve the voltage reference 3.3 volts, and also we can see the sensed current through the MOSFET, and also we have the voltage control. So here we can see that the MOSFET is in state on when start the switching frequency, the switching period here, and it's change the state to off when the current sensed through the current sensed through the MOSFET achieve or intersect with the compensation ramp, then the MOSFET is in a state off. So and this is how the peak current mode controls operate. And here you can see that our design is stable. Also in SmartCtrl, if you have, you can see some different transfer function, like for example, the input impedance of the converter, and also you can see the transfer function of the output impedance and also the audio susceptibility. So this is all for the peak mode control, and if you have any question, please let me know. Also, I want to mention that this webinar is based on the tutorial that I mentioned before, that is inside in the installation folder, is the tutorial number 10, that it's called the peak current mode control. So if you have any question, please let me know.